Okay, we're going to look at or summarise everything in this lesson that you need to be aware of with linear transformations. Okay, the first things we've looked at is a reflection, I think. Reflection. Then there's a rotation. Then there's an enlargement. Then there's a stretch, and then there is something called a shear. Now, believe it or not, if you were an international student, you would have to do shears in and matrices at GCSE, international GCSE. So, okay, so it's harder. Right, enlargement scale factor in both directions is the same, but a stretch is when they're different. Generally, you're keeping one fixed and you're moving it parallel to the y-axis or parallel to the x-axis. Okay, and there's something special that happens. Right, in each case, we are just looking at the original. In fact, I'm just going to draw it as a box. Okay, the original box, which is a 1 and 1. Okay, and we are initially, as I've told you before, just looking at the vectors, these two vectors, the I vector and the J vector, and we do the I first of all. Okay, so we're going to look at that. So we've talked about this before. If you want to reflect this in the y-axis, so reflecting, I can't bother to write reflecting, so y-axis, you can predict what's going to happen. The matrix that's going to make that happen, the transformation matrix, is going to be, well, that point there we do first is going to be over here, which is -1, 0. So that's going to give you -1, 0. And that point is going to stay the same. So that is going to be 0, 1. If you want to reflect in the x-axis, you will have to multiply by the transformation matrix. Well, this 1 by 1, which is the identity matrix, basically, if you think about it, it's the identity matrix, is going to need to be made into, the x will stay the same, so that is going to be 1, 0, but this time this is flipping down here, so that is going to be 0, -1. That's a reflection in the x-axis. Reflection in the line y equals x. Y equals x goes right up here. So that will become this. Okay, so that will be 0, 1. And that will become this, which is 1, 0. That's a reflection. See how easy this is in the y-axis. And then finally, a reflection in the we're doing the basic ones. So y equals -x. Well, where will these end up? Always do your x first. If -x is going to come down here, so that is 0, -1. And this is going to come down here, which is going to be -1, 0. Okay. Everyone happy with that? Right, so these are the basics that you need to just be able to spot. Next thing is a rotation. Again, starting with the basic 1 by 1 box. Okay, change to black. Right, so there's your 1 and there's your 1. Now, I'm just going to generalize this, okay, to give you the general thing. So this is basically what a rotation looks like. Okay, a rotation, and we always go anti-clockwise. So brackets always anti-clockwise. Okay, we stick with the one rule. Right, so rotating this around. So if I just rotate this box around so that it is, drawing is quite skewy, but that's the best I can do. I'm not an artist. Anyway, so if I'm going to spin this around, that's an angle of theta. There is an angle of theta there which means there is an angle of theta there. And as we've discussed before, this dimension was originally this dimension, so it is still 1. And by splitting into components, drawing a vertical line down there, you know that this original 1, 0 vector is now this length, which is cos theta. And this length is still positive, it is sin theta. This length, however, if theta is there, is a negative, and it is outside the pinch, so it is sin theta. And then the height that this drops to will be cos theta. And that is a general rotation anti-clockwise, and theta being the angle that you're rotating around. And because of cast, if that's an obtuse angle, it'll make that negative here, but and if it's obtuse, that will stay negative. If it's obtuse, that will be a positive, and it's obtuse, that will be negative. So when you're in this rotating all the way around to an angle, so you're going to get the box over here, you're rotating by an angle that's obtuse and into this quadrant. You can see how it affects the signs of the overall thing here. Okay, and they generally do it by special angles, and I gave you a list of those special angles, so you'll recognise when you see root 2s, 1 over root 2s, root 3 over 2s, and halves and all that. Okay, and our enlargement was what we're looking at today, really. We start again. Okay, and by the way, that's a rotation about 0, 0. Okay, right, here we go. We've got original square, blah and blee. Change colour. We've got, again, 1 and 1. Now, in enlargement, if I use a scale factor of k, then that needs to be stretched out by a dimension of k. K times 1 is k. And because it's enlargement, you need to do the same in this direction, so it is k. You end up with a bigger box like that. So the coordinates of an enlargement, so enlarge meant from 0, 0 of scale factor equaling k. Okay, everyone happy with that? So what it will look like is basically, you tell me what will be here. K0, and then it will be 0k. Okay, I do want you to spot something else going on here, so I'm going to quickly adjust this and move down the page. No need to write this down because it's going to come in the next couple of sets of notes, but I might as well tell you while we're at it. Okay, right, if I just go down here, and we'll no need to draw this this out. So if I've got an enlargement here, so there's my original 1 by 1, and I do that, enlarging this shape by the matrix 3, 0, 0, 3. We all know the effect of that, do you agree? It's going to make it 3 bigger. Now if you didn't know that, you times it by this here, which is 1, 0, and the coordinates here is 0, 1. Okay, and you can see it's going to give you, that's why it gives you the 3, 0. Happy with that? So we know those are the coordinates where it's going to end up. Right, so it's over here and up there. Now what's the area of this box here? It is simply 3 times 3, which is 9, and the area of that box there is 1. So if you're using, as you learnt at GCSE Maths, a linear scale factor of 3, then the area scale factor will grow at a rate of 3 squared, which is 9. But there's something also going on here. If you take the determinant of this, and it applies to any kind of enlargement, not just ones that are from the centre, if you take the determinant of this, 3 times 3 is 9, take away 0 times 0 is nothing, so you can get the area scale factor by looking at the determinant. Okay, so that's just with that. We will have notes on that later on. I just thought I'd mention it while we're at it.
So it's the scale factor, but not the area, which is in that case it's 1 times. Whereas if the original box was 2, it was like that.
because your times by the scale factor is 9. The area of that original 2 by 2 that you're talking about would grow at a rate of 9 if you're doing a timesing it by 3, 0, 0. Yeah. All right. So if you're going to times it by that enlargement matrix, then it's going to linearly grow in both directions at a rate of 3 and 3. So its area scale factor, even though you're doing a box of 2, 0, 0, 2, will have an original area of 4, but it's going to be a new area of 36, because the determinant of what you're timesing it by is 9. Okay, right, coming back up to here, right, a stretch. So again, we're going to draw a set of axes out. Okay, and we're starting off with a 1 by 1 as per usual. And 1 and 1. I'm going to stretch it in one direction. Okay, you can, as long as if these two are both the same, it is equal in both directions. Therefore, it's a true enlargement. But if you stretch it so these are different, you don't just have to do it in one direction. You can do it in both directions, but differently. Then it's a stretch. Okay, so you can see that if I stretch this by a factor of k, but this one by a factor of I don't know why I come up with these letters, A, then you end up with something that is now not the same. Okay, so we're going to look at this. That's a stretch. So what am I doing? I'm stretching parallel to the x-axis by a factor of k and the y-axis by a factor of a. So what I will write that down. It's a stretch by a factor of k parallel to x-axis and a factor of a parallel to y-axis, and you will end up with something looking like this: k0, 0a. Okay, now as discussed just down here, what will be the new area? Well, if I just give you an example, if I give you an example of this, you can see this still works. Okay, I'll come back to that writing in a bit. If you say we get the original and we now stretch it by, let's say, 5 in this direction but only 3 in that direction, so 5, 3, you realise that the area of this new box is going to be 15, the area of this is 1, and you can see that the scaling of this would be 5, 0, 0, 3. The determinant of that is 15. So you can see, just stretching, you can see how the area is growing. Okay, yeah, but that was all it will tell you. If you don't see what this, you won't know. If you're just given a result, a final answer, and the original, you can find out what the scale factor, area scale factor it grew at, but it could be a stretch in both directions. It might not necessarily be a true enlargement, so you can't do anything more than that, if that makes sense, unless you're given some information. You can't predict what these numbers are going to be because you can't guarantee they're going to both be the same unless you're told. Right, so that's that one there. Now a shear, a shear's a weird one. Okay, and I'll come back to the notes to complete them. I dug this out and I thought it was quite. I looked the other day and I'd look at this and I thought it was quite good. So let's get past all this malarkey. Blah 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 blah. Right, what's that following? Right, okay, let's just go on to this again. So a stretch factor of 3 where the x-axis is invariant. I'll go back to a few more questions. Here we go. Right, let's go back to the beginning. Okay, this, believe it or not, is IGCSE. Okay, so here we go. So as I've just been saying, you start with a box and you're enlarging it by new images now. A dash. Well, they actually call this prime at university. A prime, B prime. They do that in science. I've got no idea what they do in science. But yeah, A prime, B prime. I might call it dash, because that's what it bloody is. Okay, so this is your image, right? So in this example, ABCD has been stretched to give this. The points on the y-axis have not moved. So the y-axis, or x equals 0, is called the invariant line. Okay, and we need to clear this up. Invariant line. It's not an invariant. Let's get this. What's the other format? A line of invariant points. A line of invariant points is where the points don't move. Whereas an invariant line, just to make sure we clear that up, invariant line is not necessarily points stay the same. They can move somewhere along that line. But where you say line of invariant points means that the points stay do stay where they should be.
So in an invariant line, the points stay on that line.
Yeah, anywhere on the line. So they haven't, to me, they haven't called that correctly, because it is going to stay on the.
XD dash and A dash, they move along the y-axis. The y-axis will still be an invariant line.
It will be yeah, as long as you're if you're on that line. You mean
you have to be on the line to be invariant line.
Yes.
And they don't have to move for it to be a line of invariant points, but they're different things.
They're different. Yeah. So they have to have the same, retain the same position. Yeah. Okay. So that, to me, should really be called a line of invariant points, because if you're on that line, you stay on that line. Okay, but there you go. Next, what you say? The perpendicular distance of each point from the invariance line has doubled, so stretch factor is 2. Next thing, it says draw the image of ABCD after a stretch of scale factor 2 with the x-axis invariant line. Well, that's quite clearly. Okay, this stays put, and then this stretches up. Okay, so blah blah blah. That's what we get. Draw an image after ABC after a stretch with 3 with the y-axis invariant line. So it's going to stretch out here 3 times all the way out there, with this staying put. Okay, next one. Okay, 3 going up, straight forward. Right, next one. The following diagram shows a stretch where the invariant line is not the x-axis or y-axis. Okay, so you can see that here is 2, and here is 2, 4, 6. Okay, so how do you do this one? The height's retained, so which direction is it moving parallel to? The stretch is moving parallel to the x-axis, so it must be vertical lines of x equals some number which is remaining invariant. Do you agree? Yeah. So if I was here somehow and that was 1, okay, then that is now 3, for instance. That distance from here to this point here on the original red thing to B is 3, and you can see that's grown by 3. If you chose this, you can see it doesn't work. Look, 2, and you've got 4, so you can say a scale factor of 2, but this one here is 4, and it'd have to be 8, and it's not 8, so it's not from this line here. Okay, right, as I've just been saying, so A prime, that is 3 times A, so we know it's a scale factor of 3. We knew it was a scale factor of 3. So, yeah, you can just measure from this distance here. Okay, you know that this distance here is 3, and you know it should be 9. So 3 back from here tells you where it'll be. Okay, so the stretch factor is 3, and therefore the line's got to be x equals 1. So the perpendicular distance of each point from x equals 1 has trebled. So the invariant line is x equals 1. Okay, right, next one. If the scale factor is negative, then the stretch is in the opposite direction. Okay, so, press that by accident. You start by measuring any of these, not that because it's not a stretch. These lines here, you wouldn't do the diagonal, you could, but you count horizontal and down to it anyway, so you might as well just do this. 2, and it's 4, so you can see 4 divided by 2, image divided by object gives you a scale factor of 2. And it's been stretched in the opposite direction. Okay, and if that's the case, it's going to be negative. right? So the stretch is -2. Now, you need to choose where it is, okay? Can you see that this distance here is 1 in that direction, times it by -2, measures from here, but back on yourself. So it looks like it's going to be the y-axis. See here, this is 3, times that by -2 gives you -6, and you can see it's at -6. So it seems like the y-axis is the invariant line. Yep.
But we haven't given an invariant line where the invariant line is not perpendicular.
Right. I've seen questions where no, they're generally
Is it not perpendicular to the y-axis?
no. You're going to get things that are harder than this that are going to involve. Well, no, sorry, I'll rephrase that. It's only it's only really touches on it at this level. Okay, so no, I haven't seen questions to do with stretches in any other direction. Okay, so I haven't seen any questions in exams of old, etc. So yeah, you would just treat it the same. Okay, but I haven't honestly seen any questions. I've dug around, so not to mean that they can't ask it. Same technique, you get the scale factor. If it's reversed, it's a negative.
Could you apply a linear direct line transformation like a rotation of quick first?
Oh, you mean a combined?
Yeah.
Yes, but they would again they'd tell you it's a combined as opposed to a single transformation you're looking for. So they're not going to make it too onerous because at the end of the day you've only got certain times. I've just realised this a while back, is that the questions you do, some of them are quite complicated, yeah, when you're being taught. However, there's only a certain amount of time you've got, so they won't, like, you know, the alpha betas, some of the alpha betas, they're not going to ask you something like, I can't imagine they'd ask you something like, what is alpha to the power of 4 plus beta to the power of 4, because the expansion of that is quite awkward. And it'll take a lot of time. They don't want you to waste the time. They just want to know, can you just do it for the basics? We assume that if you can do it for the basic, you could figure it out for the harder bit. Does that make sense? And a lot of maths is going to be like that, as you need to be taught fully and practice it here, so that in an exam, do you understand the basics? And then you go to university and stretch that bit further. Yeah. The perpendicular distance of each point is from the y-axis has been doubled. So the invariant line is the y-axis. Right, shears. In a shear, all the points on an object move parallel to a fixed line called the invariant line. Okay? A shear does not change the area of the shape. Okay, that's worth. It doesn't. You're going to see. It's not going to. Yeah. It's not going to affect its way. It just shears it across. The areas are retained, you know, the same. Okay. If you give a triangle, the base. I'll give you an example. The base is the same, and the base will remain the same because if you're shearing it, you're pulling this across over here. Okay. The base will stay the same because it hasn't been sheared, but because the height is the same across. The area doesn't change. Right, here we go. To calculate the distance moved by a point, use this formula. Okay, the shear factor, it's worth writing this down. The shear factor is the distance moved by a point divided by the perpendicular distance of point from invariant line. It's the perpendicular. So if you bring that up and put it to here, times it by the shear factor. So you times the shear factor by the perpendicular distance of a point from the invariant line, and that will give the distance it moves in that in the direction. Okay. So that's an important formula there. Now this isn't in the book, and I haven't checked yet whether they've omitted it on purpose because it's not on the course. But it seems stupid not to cover it now, especially if International GCSE is covering it. At least you'll know what it is. Okay, here we go. So you got that down? Perpendicular distance measured from the point of the invariant line. Right. So here we go. Right, in this example, ABCD has been sheared to give ABCD, as you can see here. Okay, the points on the x-axis have not moved, and the reason they haven't been moved is the x-axis is called the invariant line. Okay, so it's a very easy example. Look, can you see that that's got no perpendicular distance from the invariant line, the x-axis? So times by the shear factor is going to have no effect. However, that is 1. Okay, perpendicular distance is 1. So the shear factor, looking at this, is what? 1. Because you've now moved that, a perpendicular distance of 1, so it's now moved across 1. That is a perpendicular distance of 1, so it's now moved across 1. And that's why you get this shape here. So D prime is equal to 1. Okay, the distance from there to there is equal to 1. And the distance from D to the original line is 1. So from that previous slide, distance travelled divided by the perpendicular distance from invariant line is 1 divided by 1, so the shear factor must be 1. Okay, so shear factor is 1. Now these get slightly more complicated, so here we go. Draw the image ABCD after a shear factor of 2 with the x-axis of the invariant line. So again, A and B will stay the same, do you agree, if that's the invariant line? But this point just here is 1 up. That is now going to be scale factor of 2, so we're going to times it by 2. Perpendicular distance times by the shear factor. So that is now going to go across to here. Similarly, that point is 1 up, and it's going to go across here. So where it was originally, which was there, it's now going to be sheared across here by 2. So 1 up, it's going to go 2 across. So we're going to get that kind of situation where that is nailed shut and that is pushed across. Now, that forms a parallelogram, but the area of that is the same as the area of that. How do I know? What's the formula for a parallelogram? Base times perpendicular height. Okay, so you can see that if you did this by what do you call it, Pythag, you can see that this would be 1 up and 2 across. So that length there would be root 5 going up there, is it? 1 and 2, root 5, and then this vertical height. Is that the best way of doing it? It's probably not the best way of doing it anyway, is it? 1 across and then time. Yeah, of course. Amy, just ignore what I've just said there. It's embarrassing. But anyway, I could use that as my parallel line and times it by the perpendicular height, which is 1. Okay, 1 times 1 is 1. That area is 1. The original is area is 1. A shear will never change, and that's how you can spot it also, will never change the area, okay, the original area. Oh, what's happened? Oh, it's a different question. Right, draw the image ABCD after a shear factor of 1 with the y-axis of the invariant line. So as you can see, this points on this line don't move, so that has got no perpendicular distance. That has got a perpendicular distance from the invariant line of 1. Scale factor of 1, that's going to move to where C is. That's going to move over here. So draw it back to the original, and that's what we end up with. Okay, next question. Draw the image after scale factor 2, blah, 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 so we know it's going to be there. Areas are the same. Now, describe fully. Okay, so no longer are we on the invariant line. Okay, the shape is away from the invariant line. So the distance?
The formula, distance moved by the point is parallel to the perpendicular.
Yeah, yes. Okay, good point. Well, as long as I get one, I don't care. You can then toss up between who wins from rock, papers and scissors, and that's the main thing. Or I can even do a heads or tails. Or Sasha might say, oh, I don't. Or Tom might say, I don't like currants. We're saved. Or what's in there?
I made up those raisins.
Oh, there's no raisins.
There's fruit in them.
Who's volunteering? Is anyone volunteering not to have one? There we go. We're sorted.
We will have to give money to get a charity.
Yeah, I've got money in my bag.
Right, can you see the invariant line? Okay. There's a way of finding the invariant line, you lot. Oi, I don't like the idea of you having the choice first and I'm getting the last one, what people don't want.
I'll give you 50 feet.
Thank God. Honest to God. That's the wrong way around. And if Amy was there, I probably wouldn't be allowed it. What's going on with that one? Hey? Yeah. Okay.
So you need to give Elliot that carry.
No, those are that's going to charity as it is. That's what you call it.
Get you a second.
That is uniform, non-uniform money. Thank God Amy wasn't here. I'm just stuffing my face with a cake. Okay. No. Bloody hell. It was like you dislocated your jaw there. Right. How you can find the invariant line. You watching this, you jokers? See this line here? Okay. It was this originally. Now if you draw a dotted line down here and a dotted line down here, they will both coincide to where the invariant line is. Same as if you drew down here, it won't land on the same point as before, but it will land on the invariant line. You can see they both go down to the invariant line here. So the invariant line, it's worth making a note to yourself there. How can you say that in English? Two corresponding sides, lengths, okay, on the original and the image. If you draw those down, they will coincide to where the invariant line is. Okay, so it's a shear. It's not a stretch because this is the height hasn't changed, but the area hasn't changed. No, they don't coincide on the same point, Lewis. Look, can you see this goes down over here, and this comes down over here, whereas this one comes down to here, and this one comes down to here. So we've got one here and one here, so they're just lying on the invariant line, okay? Right, now, what's the shear factor? Well, let's pick on any point. So I'm going to pick on this point here. The original was 4 up, okay, and the distance it's travelled is, what's that? It's 8, isn't it? So perpendicular distance, distance travelled parallel to the invariant line is 8, divided by the perpendicular distance from the invariant line, and that is 4. So the shear factor is 2. Okay, and as you've got here, look, drawn down, and the invariant line is the x-axis, you'd need to say that, and the shear factor is 8 divided by 4, which is 2. Okay? Right, describe fully the single transformation that takes A, B, C, D to A prime, B prime, C prime, D prime. Well, you can see it is parallel in this direction. Okay, parallel to the x-axis, so it's a y equals. It might be the x-axis, it might not. Let's have a look. You draw these lines down here, and they coincide with that there. So that is the invariant line. It's a shear. Okay, the invariant line will be y equals 2. And the distance is, well, if I do this, I'll do this point up here, that is, what's that going to be there? 2 going up to 9 is 7. And going across here is 1 to 8 is 7. Okay, 7 divided by 7 is 1. So the invariant line is y equals 2. The shear factor, scale factor, is going to be 1. Okay, so done that. Right, y equals 2, invariant line, blah blah. Shear factor is 1 divided by 1, 7 to 7 is 1. Okay, there it is. Right, describe fully the single transformation that takes ABC onto A prime, B prime, etc. Okay, right. How do I go back now? There. Can you see they're pushing away along the positive x numbers? right? Because you can have a shear scale factor of negative, which will be pushing along back on itself over in this direction, okay? So it's very important that you understand that. This one here, you can see it's moving parallel to the y-axis, so it's going to be x equals a number, or it could even be the y-axis, right? But importantly, we are going in the positive direction, so it's a positive shear. Now, where is it? Well, that line there, okay, that line there, B2 prime there, goes onto there. So let's just see what's going on here. So what is it? 4 and 1, 4 and 1 over here. And you can see that's going to be the same there, isn't it? Oh, I'm going to let him draw on it because I can't see it. I don't think yeah, it is. So there. So it's a shear, and the y-axis, or x equals 0, is the thingamajig. And the distance, well, that's, what should I do that one there? 4. Okay. And that has moved to there, which is 2. So it's going to be a half. Okay. Right, next one. Now, when you get this going this way and this going this way, where's the invariant line, do you think? In the middle somewhere. Okay, and because these points here stay the same on the original shape, that must be the invariant line. Okay, do you agree? Okay, so if you drew C to B prime, C to B prime, they meet just here. Okay, same again. If you did D to A and D prime to A, you can see they meet here. So that is the invariant line. They've been, and it's parallel in this direction. So it's a shear. What do you call it? The invariant line is y equals 6, and it is perpendicular distance. Pick on this. Perpendicular distance is 3 and 3. It's 1. It has moved in the positive direction, and because you're going to below it, that is still the positive direction. Okay, so it's a positive 1 shear factor. Okay, invariant line is y equals 6. I think I said x equals 6. No, I said y equals 6. Shear factor, as I said, is 1. Okay. Now here we are, original shape, and we're going back on ourselves. So same thing applies. C to D comes back here and there. So you can see blah, 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 blah. The invariant line is x equals 1. Okay, so x equals 1, but the scale factor going back on yourself this way is going to be a negative. So the distance here is 7. Okay, and it has moved, and I think that's 7 down there, 8, and 1 up 7. So the scale factor is minus 1 because you've gone in a negative direction up to the y-axis. So it's a shear. It was x equals 1. Notice the negative shear because you're going in the wrong direction. Positive, you would go along the positive x-axis. Okay. Right, x equals 1 invariant line. Shear factor is going to be that divided by that. So pick on any point, it gives you minus 1 because it's a negative shear. You're going in the wrong direction. Okay. Has that covered shear? What's special about shear's area? It's always the same. Okay, so there we go. I thought that was reasonably quite good. Now, how do you spot it? Was cleaning up, bit of housekeeping. How do you spot it? Okay, right. So if we're going to just look at this now, bang, bing, ding, da. We start with our original 1 by 1 as we usually do. Okay, you're watching original 1, 1, 1, 1. Right, I'm going to shear it parallel to the x-axis is the invariant line. I'm going to use a scale factor of k. So where will this new point go? Well, that's a distance of there, so it will go over to here. That's 1, so it will go over to here. So it will stretch like that. Right. Enlargement, yes, because you can draw it from the 0. They all have to go through 0, 0. Yeah, okay. Right, because it's spreading out from the 0, 0. It's a point worth noting. I think, what is it we're doing today? I can't remember. enlargements, right, so enlargements comes onto it. Right, so the new one would be shearing, a shear, where the x-axis is the invariant line, invariant, what? Invariant line, okay? You will end up with, a shear with a shear factor of k. Okay, so what will it be? Well, I did it as 1 there, didn't I? If I did it as k, so that would be k across. Do you agree? So 1 up, it would be k. So I'm going to rub that out actually and do it so it's random over here. Then that would be a distance of k. Okay, you happy with that? That point will be that point just there. That point stays the same. So let's look at the original vectors. That one stays the same, 1, 0. But this one has become that one there. So it is going to be K, K1. Do you agree? Yeah. So you can spot a shear because you'll have 1, 1 and a number here. Watch me now. If that wasn't 1, 1 and that was A, what has gone on? Two things have gone on. Not stretched. Enlarged, because I've used the same thing here. It's enlarged by a scale factor of A and then being stretched by a shear scale, sorry, not stretched, a shear by a scale factor of K. Yeah? If I did that, what would that be? A stretch with a factor of that in the X direction, factor that in the Y direction, and then a shear. Right, and that's going too far, but you can see what I'm talking about, yeah? 1, 1. Happy with that? Okay, so I've written that down there. Then the last one that we need to do is a shear factor of K. Right, and in the same sense, you can see what's going to happen. A shear with the y-axis as the invariant line. With a shear factor of K. Well, you can see if the y-axis is it, then the y-axis is going to stay the same, 0, 1. But this point here is 1 away. It's going to be K up here. Okay, don't want to draw it up there because it looks messy. So you can see it is going to be 1 across, but K up on the y-axis. Right, happy with that? Right, that's everything we need to do. We're going to go back onto the notes after all of that. Does that make sense? And so you can spot all of these, what's going on. They all look different and unique. Right, here we go. Let's see what the questions are. K on the... I didn't draw it, but if I said it would look messy. If I was going to draw it, obviously, that would go to K just there. And then it would go across like that and come back down to there. Right, going back to the notes. Right, enlargements and stretches. You can describe enlargements and stretches using linear transformations. So if the matrix is 3, 0, 0, 2, find the image T prime of triangle T with vertices blah blah bling bling blee blee under the transformation of M. So what you would do is you do A. 2 minutes, well, I was going to quickly do this one then. We've got 3, 0, 0, 2. Can you see it's a stretch? You can look at that now and see it's a stretch. 3 parallel to the x-axis, 2 parallel to the y-axis. Okay, so it's a combined stretch, right? And The vertices of the new of the original shape were 1, 1, 1, 2, 2, 2. So our new positions will be 3. That times that is 3. That times that is 3, and that is 6 because it's all trebled. However, the y's are doubled. 2, 4, and that times that, you can see it's 4. So it is as you would expect. Sketch them on a graph. 2 minutes. I can't be bothered. We're going to stop there. We'll go over those notes next lesson.